Section 7.6 First order differential equations. In this section, we see how differential equations can be used to model several real-world applications. We review separable differential equations. These are equations that can be expressed in the form dy over dx equal fx over gy. To solve such equation, first separate the variables in the differential form gy dy equals fx dx and integrate both sides separately to obtain the integral of gy dy equals the integral of fx dx. The goal of this section is to examine a second class of differential equations called first-order linear that have the general form dy over dx plus pxy equals qx. In this type, first order means the highest order derivative is 1 and linear means the highest order of the unknown function y is 1. For example, the differential equation dy over dx minus y over x equal exponential of minus x is first order linear with px equal minus 1 over x and qx equal exponential of minus x. Another example is x squared dy over dx minus x squared plus 2 multiplied by y equal x to the fifth. This equation can be put in first order linear form by dividing by x squared to obtain dy over dx minus x squared plus 2 over x squared y equal x to the fifth divided by x squared. As a result, px equal minus x squared plus 2 over x squared and qx equals x cubed. The first order linear differential equation has a general solution given by yx equal 1 over ix multiplied by the integral of ix qx dx plus c, where ix equals exponential of the integral of px dx. The exponent is any antiderivative of px and c is an arbitrary constant. The function ix is called the integrating factor. Here is an example of a first-order linear differential equation. Find the general solution of x multiplied by dy over dx plus 2y equal x multiplied by exponential of x cubed. As a first step, divide each term in the given equation by x so that we can use an integrating factor. We obtain dy over dx plus 2 over x y equals exponential of x cubed. For this equation, px equals 2 over x and qx equals exponential of x cubed. The integrating factor is ix equal exponential of the integration 2 over x dx equals exponential of 2 log n x equals x squared. Thus, the general solution is y equal 1 over x squared multiplied by the integral of x squared exponential x cubed dx plus c. Substituting u equal x cubed, then du equal 3x squared dx. The integral becomes 1/3 exponential of x cubed. Therefore, the general solution is 1 over 3x squared multiplied by exponential of x cubed plus c over x squared. A first-order initial value problem involves a first-order linear differential equation and the value of y at a particular value x. Here is an example of such a problem. Solve dy over dx equal 2x squared minus 2y over x, where x is greater than 0, subject to the initial condition y equals 0 when x equals 3. To find an analytic solution, we use the integrating factor. The differential equation can be expressed in first-order linear form by adding 2y over x to both sides to obtain dy over dx plus 2y over x equal 2x squared. We have px equals 2 over x and qx equal 2x squared. An integrating factor is given by ix equal exponential of the integral of 2 2 over x dx equals exponential of 2 log n x equals x squared. The general solution of the differential equation is given by the formula y equals 1 over x squared multiplied by the integral of x squared to x squared dx plus c. The integral is 2/5 x to the 5th, so the solution y equals 2/5 x cubed plus c over x squared. To find c, note that because y equals 0 when x equals 3, it follows that 0 equals 2/5 3 cubed plus c over 3 squared. We find c equals minus 486 over 5. First order linear equations can be used to model a variety of important situations in the physical, social, and life science. We can examine a few such models as well as additional models involving separable equations. We review the exponential growth or the unrestricted growth. When the population QT of a colony is small, it is reasonable to expect the rate of change in population is proportional to the current population. In other words, dq over dt equals kq. The solution of this equation is q equals q0 exponential of kt, and it is called exponential growth. As long as the colony has plenty of food and living space, its population will obey this formula and qt will grow exponentially. When k is greater than 0, the graph of q is increasing, and when k is less than 0, the graph of q is decreasing. However, there often comes a time when the environment begins to restrict the further expansion of the colony. In this case, the rate of change of the population is proportional to not only the current population but also the potential unborn population. In other words, let B be the carrying capacity of the species. Then dq over dt equals kq multiplied by B minus q. This is called a logistic equation, and the solution is q equals b over 1 plus a multiplied by exponential of minus bkt. The graph of this solution is shown in the figure. Note that the curve has an inflection point where qt equals 1/2 b. This corresponds to the fact that the population is increasing most rapidly when the current population equals half of the capacity. Note also that when t goes to infinity, qt approaches b, thus the population approaches the capacity in the long run. One example of this model is the spread of an epidemic. Another growth model is called limited growth. The assumption is that the rate of change in population is proportional to the potential unborn population. In other words, dq over dt equals k multiplied by b minus q. The solution is q equals b minus a multiplied by exponential of minus kt. In the long run, the value of q also approaches b. Newton's law of cooling is an example of this equation. Now we are going to model a dilution problem. Configuration 1. A tank contains 20 pounds of salt dissolved in 50 gallons of water. Suppose 3 gallons of water runs into the tank every minute, and that the mixture, kept uniform by stirring, runs out of the tank at the rate of 2 gallons per minute. Modeling the rate of change of the amount of salt in the tank at any time t. Let St denote the amount of salt in the tank at the end of t minutes. The rate of change in St is the difference of the inflow rate and the outflow rate. Because the water flows into the tank contains no salt, the inflow rate is 0. For the outflow, note that at time t, there are St pounds of salt in 50 plus 3 minus 2 multiplied by t gallons of solution, because the inflow is 3 gallons per minute and the outflow is 2 gallons per minute. Thus, the concentration of salt in the solution at time t is St divided by 50 plus 3 minus 2t, and the outflow rate of salt is St over 50 plus 3 minus 2t multiplied by 2. Combining these observations, we see that the net rate of change ds over dt is given by ds over dt equals minus 2s over 50 plus t. Configuration 2. A tank contains 20 pounds of salt dissolved in 50 gallons of water. Suppose 3 gallons of brine containing 2 pounds of dissolved salt per gallon runs into the tank every minute, modeling the rate of change of the amount of salt in the tank at any time t. Let St denote the amount of salt in the tank at the end of t minutes. The rate of change in St is the difference of the inflow rate and the outflow rate. Because the 3 gallons of brine flows in the tank each minute and each gallon contains 2 pounds of salt, it follows that 2 multiplied by 3 equals 6 pounds of salt flows into the tank every minute. This is the inflow rate. The outflow rate is 0. Combining these observations, we see that the net rate of change ds over dt is given by ds over dt equals 6. In the third configuration, we consider a mixed problem. A tank contains 20 pounds of salt dissolved in 50 gallons of water. Suppose 3 gallons of brine containing 2 pounds of dissolved salt per gallon runs into the tank every minute, and that the mixture, kept uniform by stirring, runs out of the tank at the rate of 2 gallons per minute, modeling the amount of salt in the tank at any time t. Let St denote the amount of salt in the tank at the end of t minutes. The rate of change in St is the difference of the inflow rate and the outflow rate. The inflow rate is 3 multiplied by 2 equals 6 pounds of salt flows into the tank each minute. The outflow rate is the concentration of salt in the tank multiplied by 2 gallons per minute. The concentration of salt in the tank is St divided by 50 plus 3 minus 2 multiplied by t. Thus, the net rate of change ds over dt is given by 6 minus 2s over 50 plus t. We recognize this equation as a first-order linear differential equation with pt equal 2 over 50 plus t and qt equals 6. An integrating factor is it equals exponential of the integral of 2 over 50 plus t dt equals exponential of 2 log n 50 plus t equals 50 plus t squared. And the general solution is St equals 1 over 50 plus t squared multiplied by the integral of 6 multiplied by 50 plus t squared dt plus c. The integral is 1/3 of 50 plus t cubed, and the solution is 2 multiplied by 50 plus t plus c over 50 plus t squared. To evaluate c, we recall that there are 20 pounds of salt initially in the solution. This means S0 equals 20, so that 20 equals 2 multiplied by 50 plus 0 plus c over 50 plus 0 squared. We obtain c equals minus 80 multiplied by 50 squared. Another application of first-order linear differential equations involves the current of an RL electric circuit. An RL electric circuit is one with a constant resistance R and a constant inductance L. The figure shows an electric circuit with an electromotive force, a resistor, and an inductor connected in series. According to Kirchhoff's second law, if the circuit is closed at time t equals 0, then the applied electromotive force is equal to the sum of the voltage drops in the rest of the circuit. This implies that the current IT that flows in the circuit at time t must satisfy the first-order linear differential equation L multiplied by di over dt plus Ri equal E. The solution of this equation is I equal E over R multiplied by 1 minus exponential of minus RT over L. In the long run, it means that when t tends to infinity, the current I must approach E over R. This is the end of section 7.6. Thanks for watching.